So here's 42, and I think we went over this in class. But I'll run through it again. It's a discrete random variable, and the reason for that is that there's a specific outcomes, and only 3, and they're not continuous, and they occur randomly. And why do they occur randomly? Well, they have a probability. And although we know the probability of each event, and we know what each event is, we don't know on any given roll of the dice what's going to happen. So we know all the things that could happen, but we don't know what could happen. So it's random. It's discrete in that the outcomes are not continuous, like weights or something like that, or measurements of time or what have you. So anyway, so they each have a probability. So if you roll a 6 on the first roll, then you get $40. If you do not get a 6 on the first roll, okay, and the probability of getting a 6 on the first roll obviously is 1 out of 6. If you don't get a 6 on the first roll, then that's a 5 out of 6. The probability you don't get a 6. But you get a 6 on the second roll, which probability is 1 out of 6, then you get $0. You get your $10 back. It costs $10 to play. Okay, and then if you don't get a 6 on either roll, then you lose. You don't get anything, and you lost your $10. So let's review how to put this into the calculator. So you put 40, and then 0, and then -10. These are the 3 discrete outcomes. And these are the probabilities of each outcome. 1 divided by 6, and 5 over 36. And 25 over 36. Okay, and now we're going to do a stat and calc and one variable stats, and we'll put in L1 and L2 because L2 is the count, if you will. We hit enter, and so X bar is the expected amount of money that you will win, which is negative 0.2777 going on forever. So you can expect to lose 28 cents each time you play this game. And down here is the standard deviation, which is 18.331. We'll round that to 18.33. So the standard deviation is $18.33, and it's big because of the spread of the game. It goes from $40 to -10, and that's about it. Okay, so here's the probability model right here. Okay, and then here's the breakdown of the discrete random variable, and then here's the probability model. Here's the mean and the standard deviation. Now, if you play 5 times, the mean is 5 times -28, which is -$1.40. Standard deviation is the square root of 5 times the variance, which is $18.33 squared. And so the standard deviation for 5 plays is approximately $40.99. Now, if you play this, if 100 people play this, what's the probability that they'll all, in aggregate, they'll lose money? Well, you put -28. Say the expected amount of money lost is -28. The standard deviation is $183.30. So you put -28 in the center, and then you put 0, and that's the point at which that's the break-even point, losing money versus making money. And find the z-score for 0, which is 0.1527, 28. Okay, it's 0 minus negative 28, which is 28, over $183.30. So that's approximately 0.1527. You do a normal CDF from negative 99 all the way to 0.1527, and you get 561. So that's the probability that the people running the game will make money with 100 people playing, with a 43.439 probability that they'll lose money. Okay. And you can also solve this problem using a sampling distribution, which I do here. And it comes up with the same answer. All right. Number 48. Okay. The bags are supposed to contain 10 ounces. The machine is set at 10.2 to put 10.2 ounces in every bag with a standard deviation of 0.12. A bag is underweight if it is 10 ounces or less. So we'll use a population distribution to find the function of all bags, find the fraction of all bags underweight. Okay, so that's the first question. What fraction of the bags are underweight? Okay, so 10.2 is the mean. That's the amount that's distributed by the machine. 0.12 is the standard deviation, and we find out where is 10. Any bag that has less than 10 ounces is going to be underweight. So what's the z-score of 10? Well, z is y minus mu over sigma. 10 minus 10.2 divided by 0.12 is approximately equal to negative 1.67. And so the probability that a bag is going to weigh 10 ounces or less is a normal CDF negative 99, comma negative 1.67, or about a little less than 5%. Okay, now, if you buy 3 bags, what's the probability that none of them are underweight? Well, what's the probability that a bag is not underweight? It's 0.925. In other words, 1 minus 0.0475. So if you cube that, you get 0.864. The probability that no bags are underweight out of 3 is 0.864. Okay. Now, what's the probability that the average of the 3 bags is less than 10 ounces? Now, you think, well, 3 bags, that's a really small sample. I mean, you know, it's really small. Well, yeah, it is. However, we're told that the population is normal. The population of these potato chip bags is normal. So, therefore, it's reasonable to assume that the 3 bags are random and independent. 3 bags is less than 10% of all the potato chips bags. Now, there's not an NP and an NQ. This is not a proportion problem. This is a quantitative problem. And since we are told the population is normally distributed to begin with, an n equals 3 is big enough sample to have a normal sampling distribution. And sampling distribution is going to be approximately normal, 10.2 comma 0.12 divided by the square root of 3, or 0.0693. Okay, so we find the z-score. The z-score is going to be 10 minus 10.2 divided by 0.0693, which is approximately equal to 2.887, which is a pretty big z-score. So the probability that the bags will average, less than 10 ounces, is really small. Definitely less than 1%. Okay, now what about 24 bags? Use a sampling distribution, same preconditions apply. Approximately normal, mu, comma, sigma over the square root of n. This is the sampling distribution for quantitative data. So n equals 24. So we're going to have an approximately normal sampling distribution of 10.2 comma 12 over the square root of 24, or 10.2 comma 2.4495. Okay, so the z-score equals y minus equals negative 0.2 over 2.4495, which approximately equal to 8.165. That's a huge z-score. It's very unlikely that this will happen. Okay, 51. Okay, first we got to do 49. Skewed population. Mu equals 9.6, sigma equals 5.4. A, cannot use a normal model since the distribution is not normal. Okay. B, n equals 4 is not big enough for the approximately normal sampling distribution. What is the probability that y bar is greater than or equal to 15 when n equals 10? Still risky, but the sampling distribution is going to be 9.6 and then 5.4 divided by the square root of 10, with a z-score of 15 minus 9.6 over 1.7 is greater than 3, so that's unlikely to happen. Okay, so that was 49. So let's look at 51. Okay, the total, what's the probability of the total that's greater than or equal to $500? Okay, with 40, remember this is tips. Okay, so and when n equals 40, that's 40 dinners. Okay, it must average 500 divided by 40, which is $12.50. So we use a sampling distribution. Customers are random and independent. N equals 40 is big enough for a sampling distribution to be approximately normal, even if population is not normal. 40 is less than 10% of all customers. So we're going to end up with an approximately normal sampling distribution of 9.6, comma 0.8538. Okay? So 9.6 is the average amount of tip per dinner. They have to average $12.50. It's going to be 12.5 minus 9.6 divided by 8.8538. You don't have to be a genius to see this is going to be greater than 3, a really big z-score. So the probability that their tips, that they'll make $500, that the tips will average $12.50, is, look at this. It would happen, like 3 times out of 1,000. Okay, it's not going to happen. Okay. Now, 54. All right. Assume a normal model for milk production for both types of cows. Ayrshires are approximately normal for 47 pounds of milk with a 6-pound standard deviation. This is for the population of these cows. Jerseys are approximately normal with a mean of 43 pounds and a standard deviation of 5 pounds. What's the probability that a random Ayrshire averages greater than or equal to 50 pounds? Okay, now we're using the population. We're not using a sampling distribution. We're using the population because we're talking about one randomly selected cow. So 47's in the middle. We're going to use a normal model because it's a normal distribution. We're told that. Okay, so we put down 50, and we want to know the z-score of 50. So what's the probability that it averages more than 50, greater than or equal to 50? So 50 minus 47 divided by 6 is 0.5. So the probability that the average pounds are greater than or equal to 50 is the normal CDF 0.5, comma 99, which is about 31%. So 31%, 0.31 probability, 0.31 probability that the milk averages more than 50 pounds, that the production averages more than 50 pounds on a daily basis. Okay, what is the probability that a random Ayrshire gives more than a Jersey at a randomly selected Jersey? So we're doing the expected amount of the difference, or symbolized by delta, which is 47 minus 43 equals 4. And the standard deviation is going to be the square root of the variances added together. Square root of 6 squared plus 5 squared equals 7.81. So 4 is the average difference. We want to know when where 0 is. 0 is where the random Ayrshire is giving more than a Jersey. And on the left, this is where the Jersey gives more right here. And here's where the Ayrshire gives more. Okay? So we get the z-score of 0 is negative 0.512. Let's see if we work that out. Yeah, z equals negative 4 over 7.81, which is negative 0.512. The probability, so then we're going to go from negative 0.512 to 99 is probability that Ayrshire gives more than a Jersey on a daily basis, averages in terms of pounds of milk. Normal CDF, negative 0.512 comma 99, which is approximately 0.7. C. Okay. Use a sampling distribution. Since the population is normal, a sample is large enough. 20 is less than 10% of the population of Jersey cows. Assume cows are random and independent. It's safe. That assumption is safe. So a herd of 20 has approximately normal sampling distribution of 43, comma, 5 divided by the square root of 20, or 43, comma, 1.118. Okay, what is the probability that 20 cows average 45 pounds of milk a day? So we're going to put down 45 as our goal. Find the z-score, okay, which is 1.789, okay, and we'll take the normal CDF 1.789, comma 99. So the probability that the 20 Jersey cows average 45 pounds of milk a day is around 4.04, 0.0368. Okay, it's not very likely. D. What's the probability that Ayrshires average, what is the question? Average at least here, let me move down. At least 5 pounds more than the Jerseys. Okay? All right. So the expected difference is 4. Okay? Now we're talking about an Ayrshire herd of 10 cows. Doesn't matter that the size of the herds is different. Still okay. So we have an approximately normal. Still everything's normal. Nothing has changed. Preconditions still hold. And it's going to be, for the Ayrshire, the sampling distribution is approximately normal, 47, 1.897. The difference is still 4. Now, the standard deviation of the difference is going to be the square root of the variances. 1.118 squared plus 1.897 squared, or 2.2023. Okay, now the question is, what's the probability that the Ayrshires average at least 5 pounds more? So we're going to take 5. Here's 5. The average difference is 4 pounds of milk a day. So what's the probability that they average 5 pounds or more of milk a day? So it's going to be 5.5 minus 4 over 2.2023, which is approximately, the z-score is approximately equal to 4.54. So we'll do a normal CDF of 4.54, comma 99, and that's approximately equal to 0.329. So the probability that Ayrshires average at least 5 pounds more than Jerseys is 0.329. That's it.